Hello, this is the U.S. Space Force Ground Support Equipment Senior Design M6 presentation. Project advisor is Dr. Michael Kinzel, and this is part of the Mechanical and Aerospace Engineering College. So let's introduce the group members, starting with.
I'm Samuel Adderley.
I'm Alec Alba.
Xavier Alexander.
I'm Zach Rogers.
I'm Blake Santinello.
And I'm Robert Zhang.
Hi, I'm Sam, and I'm here to introduce the intent of this project, which is to quickly deploy a rocket that carries a payload of up to 100 tons of material anywhere in the world. And this process has many logistical concerns and multiple processes, which is why it is required that we've worked with other groups to achieve this task. One subset of this task would include loading the rocket with the desired payload, efficiently reducing overall response time, which then leads to the main purpose of this group, which is to essentially create a system that facilitates the transition of the provided cargo pod into the launch vehicle, with main focuses on timing, a sound structural design and functionality, with an interfacing rocket with machine, and structural and engineering analysis and design concepts. Thank you.
Okay, so for section 2, I went over the project objectives and scope in M6. So I'm going to give kind of a brief overview of this, as it will be covered in more detail throughout the rest of the presentation. But I want to kind of highlight a couple things here that are important. So essentially, our test cases were focused on 2 major cases, along with a third subset case, which is focused on hydraulics. So for our system, in terms of how we loaded the weight or the forces onto the device, we used 2 main ways to do that. So we either used, essentially this is the top portion of the cargo pod with the lower portion just chopped off. We used a simplified version of this to allow us to load the weight as a distributed force. And then we also did it as using the hook faces here, the loading area faces, and using 4 separate distributed loads. So we wanted to see if by introducing this cargo pod piece, if it added rigidity or not to the system, and basically wanted to use this to cross-verify results as we went through. So for the first test, we see cargo pod loading, but we used everything in super simplified models, and everything was bonded together, so it was a solid body. It was treated as a solid body to the testing. Then we started introducing different contacts. So we were playing around with different frictional forces, contacts between surfaces, that kind of stuff. And we essentially tested loading of 4 hooks, so separately with 25 tons per hook. And then we did it again with only 2 hooks, so essentially simulating as if 2 of the hooks were the fail. So we put 50 tons on each hook. And then we did that again, but we used cargo pod loading with, again, 4 hooks and then with 2 hooks. And then we did a very last one using the cargo pod loading, 4 hooks, and we introduced a moment force, which would be caused by a wind force on the actual cargo pod body. That was calculated with hand calculations and then plugged back into the model in a way that made it simplified so that we weren't doing CFD along with the FEA for our calculations. So test case 2 essentially built on top of test case 1. So we combined the hooks, the frame, the arm, rails, and carriages, and we introduced geometry optimizations, reinforcements, and manufacturability additions. So this might have included cutting the frame body or the hook bodies into the actual plates that would be used for manufacture, and introducing welds in critical areas, that kind of stuff. So each of these test cases, we introduced changes such as, like I said, adding welds or reinforcements in key areas, and then use the cargo pod loading force plus the moment from the wind. So we basically used the worst case scenario for testing these once we verified that our testing setup was correct with test case 1. And then the last test case was test case 3, which just focused on testing of the supporting brackets for the hydraulic system components. So essentially just fixed these little brackets in space applied the necessary forces based on how hand calculations, and used that to figure out if the brackets needed to be, increased or decreased, and how we can improve that system. Okay, so for the third section, I'm going to cover the assessment of the relevant existing technologies and standards. So give a quick recap here of a couple of things that we went into last semester more in depth when we were trying to decide what our design was going to be based around. So we went into the benefits of free rigging versus specialized lifting equipment. This has several factors that affect it, such as time, adaptability, cost, and stability and control or safety. So we use these different factors and played them off on how it would affect our design. And eventually we decided on going with something special, with more specialized lifting equipment wise, due to the fact that adaptability wise, the cargo pod's going to stay the same and it's going to be performing the same task. So we can take a little bit of a hit on the adaptability. Obviously it's going to cost a little bit more, but if we're repeating the same task over and over, the stability and control and time factors that we're gaining by using specialized lifting really helps us out in the design and meeting the necessary time requirements of the project scope. So the next step we went into was FEA. It's kind of just a little bit of a deeper dive into some of the ways that FEA works, stuff to look out for, and how to identify certain things in results, along with different contact forces and whatnot. Another thing we went into was the safety side of it, as this is very important in any engineering design. So we went into a deeper look at factor safety, and more specifically factor safety within the industry, material selection and how it affects factor safety, and also center of gravity, such as load charts. If you get into something more free rigging crane wise, it's important to understand how the center of gravity of your lifting load affects the capacity or lifting capacity of the devices being used. So with that said, one of the main objects that I want to go into further is our decision to use Starship and Chopsticks by SpaceX. So first of all, this meets our needed cargo loading capacity. Recent estimates, being that this is still in design, are saying possibly up to even 150 tons. For this project, we were given 100 tons as our capability. So with that in mind, here's a concept view of the cargo pod opening area and what it may look like once it's complete. And then here's the actual dimensions via the SpaceX handbook for Starship. So these were the dimensions we used for measuring tolerances and clearances with both our design along with our mock-up for the cargo pod that we would be lifting. So this design here, obviously, you have a little bit of restriction with overhead lifting, so we took that into account. But at the same time, this is a very large opening, so it gives us a lot of flexibility to work with different ways to insert the cargo pod. Another reason we chose Starship was their innovative stacking method. So as you can see here, the Super Heavy booster is positioned on its launch platform, and the Starship can actually be raised up on top of and lowered down to the ground below for stacking and unstacking the rocket. And this is done on the launch pad by use of this tower and Chopsticks feature here, which these actually actuate to be able to grab onto the rocket and lift it upward. So with this in mind, this is something new to the industry that hasn't been done before, and it introduces new possibilities for cargo pod loading. And that's why we decided to go with Starship here to look at possibilities with that. So the next sections, I'm going to go into a little bit more on the prior technology and specialized components we went into, along with commercial off-the-shelf components that we ended up using in our project. So to start, we were able to speak with a couple people down at the vehicle assembly building over at KSC or Kennedy Space Center. They gave us some great advice for overhead lifting, stuff that was used, back to the shuttle days, and even in use to today, which we used as kind of a decision point in what our design was going to be based upon. A lot of this equipment is very specialized and very, very, very precise, but with that precision comes a cost of time. So that was a deciding factor that made us kind of stray away from free rigging and overhead lifting crane wise. Another thing we looked into was like elevator platforms. So for this, we looked at aircraft ship due to their loading capacity of being able to lift large capacity planes and such. So we just looked into the systems that are involved with that, cable driven, belt driven, hydraulic driven, just to get different ideas for how that stuff works. And then what we ended up deciding to kind of base a lot of our design around was actually stuff that's used in the wind turbine mast industry. So for wind turbines, they have a lot of companies are making specialized lifting devices to lift these large mast, basically the poles that the wind turbines sit on up into position due to the difficult environments of installing these in place, whether it's in the middle of a field or in the middle of the ocean. So all these devices are somewhat different, but also somewhat similar. Essentially just use an under hook grabbing type mechanism that's actuated outward to be able to clamp onto a flange or a lip of the mast itself. And most of them, like I said, are hydraulically actuated, but they do it in slightly different ways. So you can see there's some that have less overhead requirements, more overhead requirements. They can be hooked to cranes, they can be hooked to boom arms, all sorts of different stuff. So this was a good base point for us to kind of look at and get some inspiration moving forward in our design. So with that in mind, we started thinking, okay, like what do we need to research further to figure out off-the-shelf components that we can use with our design? So first of all, we started looking, okay, how do we get these to slide on a path that we wanted to follow? So we started looking to linear rails and carriage guides. You can see here, these are a couple of mock pictures of what that could look like. And essentially, we did research to figure out how to size these components. So you have to calculate the forces and degrees of freedoms and how that force will feed back into the carriage determines the sizing for that component. Another thing we looked into is hydraulics. So this was very similar to how we did for here with the linear rails and carriage guides. Essentially figure out your forces, work backwards, size your components from there. So that's pretty much what we did for those components and how we dealt with off-the-shelf components.
Hi, Sam here again, and here to talk about the professional and societal considerations. Now we've narrowed them down to about 5, which would include economic, environmental, sustainability, manufacturability, and ethical. So let's starting off with economic. We believe that due to the advanced design, due to this advanced idea and design of this particular project, it can be the lift arm can operate autonomously, which can save money in having operators and people putting their lives in danger to just everything being taken care by AI essentially. Secondly, we believe that with the environment, having the design integrated with the rocket ship reduces the need for a payload vehicle, which can possibly emit harmful gases into the atmosphere. We also believe that we've created a design that can function efficiently and has comparable and is comparable to similar structures currently in use, which means that we believe that it can last the test of time when compared to designs of old that were made by other companies. In manufacturing, we believe that we've determined that most of the components are available for purchase and are comparable in cost, and in some cases cheaper than most current designs. And lastly, this design project represents a true intent to appease the idea of pushing humanity forward and ensuring that investors and users are satisfied. This group also has followed safety and regulation guidelines to the letter, and no shortcuts were taken. We've weeded out as much that can go wrong in this design as we can, and we believe that we have put together a great design for you guys.
The design requirements for this project are to support the 100-ton payload, able to vertically lift at least 28 meters, which is the height from the base of the starship to its floor level of payload area. Rapid loading within 2 hours, have a design factor of safety of 3, operate and withstand wind speeds of up to around 9 meters per second or 20 miles per hour. Able to horizontally transport cargo pod into rocket, able to withstand corrosion resistance, and the design needs to be feasible. Concept that the team selected is the tower with external lifting arm. The assumption for this designs, which is that the Starship door opens downwards, a single cylindrical shaped cargo pod already oriented vertically when arrived on site, in a flange geometry piece on top of the cargo pod. The idea is that a cargo pod attachment device connects to one end of the arm and the other and connected on or against a pivot edge of supporting tower, like how the chopstick arm is connected to the Megazilla tower. So the arm can slide up, down, and rotate against the pivot axis to perform the lifting operation. Overall, the lifting process will look like this. Arm will lower until it reaches the top surface of the cargo pod, and the attachment device will grab or latch the cargo pod. After, the arm will rise to lift the cargo pod till the bottom of the cargo pod reaches the same elevation as the floor of the Starship or any other rocket's payload area. Then the arm rotates to move and position cargo pod into payload space. Finally, the attachment device unlatches and the system retreats. The team decided to focus on the cargo attachment device since there are already existing lifting tower technology like SpaceX's Megazilla chopstick arm lifting tower. Initial design concept has a cross-shaped X frame with sliding hooks on each branch actuated by hydraulics. The 4 hydraulics provide extra reliability if 1 or 2 hooks fail during the lifting operation. This is the initial assembled design, and the major design components are labeled in red. The cross-shaped rigid frame serves as the foundation with 4 extended branch leg where the hooks, rail, and hydraulic system are placed. Hooks are used to grasp the cargo pod, and the rails and guides are mounted between the frame and hook to provide a linear translation path for the hook. The hub is a part of the frame where the arm can be placed. The fork hook design is to provide stability for the cargo pod during lifting, to distribute and lessen the load on each hook in the leg of the rigid frame. Arm is to provide the connecting interface between frame and tower, also transporting cargo pod into payload area during lifting operation. This is the initial frame design. Material selected is the A36 carbon steel plate because high yield strength, which result in less material usage. Initial calculations were based on the preliminary design concept sketch shown in the top right corner. Hand calculation started with solid frame, then transitioned to hollow square geometry. Calculation focused on bending stress produced by the moment of payload. Each branch needs to support 25 tons, since 100-ton payload is evenly distributed among the 4 branches in the weight of hook. Initial frame design is a 0.4 millimeter by 0.4 meter, which is determined by rail and carriage configuration that is going to be discussed later. The frame is made from 2-inch thick plates, which is a commercially available size. This sizing results in a factor of safety of 6.2, which is greater than the design requirement. Hand calculations cannot account for stress concentrations since there are no stress concentration factor value available for this scenario, which need FEA testing. Filled plates are added to reduce stress concentration at sharp edges, and the hub is on the top of the frame for the placement of arm. For the hook, initial calculation focused on lower portion of the hook and treated it as a cantilever beam. Total of 4 hooks, load of 100 tons is distributed evenly between each hook, so each hook needs to support 25 tons. In the original calculation, the geometry were maximized and treated as solid. Calculations become complex quickly, so once the initial calculation were complete, a combination of simple hand calcs and iterated modeling and testing were used to trim down to the final design of the hook. As for the rail and carriages, these components are off-the-shelf items from McMaster-Carr. The key specifications are shown. The dynamic load capacity is used for calculation for a more conservative design, and it's determined that 6 carriages are required for each hook to achieve a factor of safety of at least 3. Knowing this, 3 rail with 2 carriages on each rail for the hook is designed and seen in the bottom figure. This is the most optimal configuration because greasing is required for the carriage, and the grease ports are at the ends of the carriage. The carriage can be placed back to back with grease ports exposed for easy access for grease fittings. So for the arm design, initial calculation started with A36 rounded circular profile bars, but the diameter required is not commercially available. Then research is done. Sunbelt Turner, a national distributor of carbon steel, has steel bars of up to 32 inches in diameter. So calculations are done for 1045 carbon steel cone drawn. It is determined that a truss design is required to achieve the design factor of safety to reduce the bending stress. Overall, the truss arm is constructed with 21-inch diameter round bars. After iterations of modeling, 45-degree truss angle provided the most optimal design. Then a 2-inch support plate is added in the front of the arm to reduce stress concentration at that area.
After initial sizing was done, an FEA analysis was done to provide a more detailed description of stress concentrations and to provide for future design iterations. Prior to doing FEA, geometry simplification was done specifically with respect to the carriage and rail system. Chamfers and fillets were removed, and the geometry was overall smoothed out as a way to make meshing easier. Also, prior to doing FEA, a mesh convergence study was done to identify the best mesh size to accurately model the system. A convergence criteria of 2.5 stress difference or less between 3 successive trials was used, and the element size was altered by body until the convergence was achieved.
Test case 1.1 tested the complete assembly where all the contact areas were bonded to reduce computational time and understand where general improvements could be made to the structure. A distributed load of 100 tons was applied to the top surface of the cargo pod flange, and this resulted in a setup that was too stiff, which led to a decrease in the maximum stress concentration value, shown here in the picture to the right for the hook elbow. The largest difference between test case 1.1 and the remaining cases happens to be that the hook elbow stress was largely underestimated. The minimum factor of safety for the ground support lifting equipment is 3, and this is based off the material properties of A36 carbon steel for the frame, hook, and hub, while the safety factor for the arm is based off AISI 1045 cold-drawn steel. The only factor of safety that failed was for the hook, which was found to be 2.93, which provides insufficient for this assembly test case. Test case 1.2 simulated a distributed load without the cargo pod in an attempt to see if the hooks would experience a difference in stress. Each upper lip of the hook was loaded with 25 tons each for a total of 100 tons. This model used frictional contacts with a recommended steel-to-steel greased friction coefficient of 0.23 for the surfaces where the carriage and linear rail systems met. The factor of safety for the hook elbow was found to be 2.67, which proves this hook to also be insufficient for this specific test case. Test case 1.3 replicated the same frictional contact connections as case 1.2, and the major difference was that for this case, each hook surface was loaded with 50 tons for a total of 100 tons to simulate a hydraulic system failure. A safety feature for the ground support equipment is that each hook that is directly facing another hook is connected as a separate closed hydraulic system, so that if one leak occurs and pressure is lost in a hydraulic system, then the loading process could be aborted safely. So that if it was a closed system with just all the hoses set up in series, if pressure was lost, then all 4 hooks would disengage, which could cause to be a large issue. Now, the cargo pod is handling logistically sensitive materials, and if the cargo pod were to fall, it could be an even larger safety issue for workers on site or any equipment nearby. The difference between cases 1.2 and 1.3 are that the maximum stress concentrations increase for the hook and frame, which makes sense considering that each hook went from a 25-ton load to a 50-ton load, and any sections in the direct area of a larger stress concentration are impacted more than the other ones that would be further away. The hook maximum stress location changed from the elbow to the top of the panel, and the maximum stress concentration for the hub and arm slightly decreased. The reason for this was because 2 hook bodies were suppressed, which caused a decrease in weight. but in reality, there shouldn't be a decrease since the hooks would remain on the frame when not engaged if a hydraulic system failure occurred due to a leak. The factor of safety for the hook decreased to 1.42 due to the added load.
In test cases 1.1, 1.2, and 1.3, there were significant stress singularities, particularly on the sharp corners of the carriage and slider rails and where the carriage met the hook. In an attempt to overcome these singularities, the sharp corners were filleted and tests were reran. However, this did not fully solve the stress singularity problem, and in all future trials, this singularity was not considered, and these two components were not considered for their maximum stress values.
This test case used a complete assembly with a distributed force on the top of the 100-ton cargo pod and the same frictional contacts from case 1.2. In order to create a more realistic model, a friction coefficient of 0.7 was added to the surfaces where the cargo pod and the bottom of the frame met. In addition, it was added to the surface between the cargo pod and where the hook meet. This coefficient represents the friction associated to dry steel to steel contact. The new contact locations reduced the stiffness in the model, which resulted in a higher value for the max stress concentrations on the hook elbow. The factor of safety was also insufficient for this iteration, with a value of 2.53. This case used the same force and contacts as case 1.4, and it simulated a hydraulic failure test in a full assembly. The main differences between case 1.4 and 1.5 are that the max stress concentrations in the hook frame and hub increased while the values of the arm were decreased. This is due to the loss of the weight, similar to the other hydraulic failure system, and the factor of safety decreased to 1.84 for the hook due to the increased load per hook.
The final load case for Model 1 was test case 1.6. This model combined both a force and moment loading on the cargo pod. The moment load was applied to simulate wind loading and was calculated using a pressure distribution from a 20 mile per hour wind on a uniform cylinder. The 100-ton load was still applied on the top face of the cargo pod, and the moment load was applied on the bottom face in such a way to maximally impact two of the hooks while minimally impacting the other two. This was thought to create the highest stress concentration in those two hooks and therefore lead to the most conservative estimate. This model, out of all of the 4 hook models, did generate the highest stress results in the elbows of the hook and in the hub, and was therefore used for all future simulations. Specifically, the maximum stress values for all of test case 1 are laid out in this chart. As mentioned, the distributed force with a moment on the cargo pod produced the highest stress results in the hook and the hub, and was therefore used for all future simulations. The highlighted parts of this diagram essentially show which structural members were affected most by changing the test case scenarios. The first iteration on Model 1 was test case 2.1. Test case 2.1 added brackets and welds to the hook, increased the thickness of the triangular support plate on the arm from 2 inches to 4 inches, chamfered the cargo pod to reduce contact stress between the cargo pod and the hook, and added welds to the frame to make the model more realistic. This model created high stress areas, specifically in the frame, hub, and welds, and this was due to the low weld thickness causing these high stress concentrations. The stress concentrations were located typically between the weld and the frame and between the weld and the hub. To overcome this problem, a thicker welded model was created. This had all the same dimensions as the previous iteration, except the weld was thickened from 0.75 inches to 1.05 inches. This reduced the stress concentrations in the frame, hub, and welds. The stress concentrations were still in the same areas. However, because the weld was thicker, the stress was able to be distributed over a larger area and therefore had a lower overall value. Run in parallel with test case 2.2 was test case 2.3, in which triangular support plates were added to the frame to increase its rigidity. This had higher stress values compared to the thicker welded model alone, as the triangles interrupted the weld matrix. The maximum stress values in the weld shifted from its location on the hub to being between the interface at the triangular support and the weld. In test case 3.1, the triangular support model was iterated on by filleting the edges of the hook and hub and reducing the overall frame thickness in an attempt to reduce weight. The fillets increase the stress concentration in both the hook and the hub, and the frame stress increased markedly in comparison to case 2.3. To investigate the effect of decreasing the frame thickness, test case 3.2 was run. In test case 3.2, the frame thickness was increased back to its original size, and the fillets in the weld or in the hub and hook remained. This test case showed that the fillets were the cause of the stress increase, as in comparison to test case 2.3, test case 3.1 and 3.2 both had higher stress values in the elbows of the hook. The frame thickness had an effect on the overall stress value in the frame. When restored back to its original value, the stress in the frame was returned to its original value as well. The supports also decreased in stress from test case 3.1 to 3.2 because the frame was thicker, and since the frame was thicker, the load bearing capacity of the frame increased, needing less rigidity from the supports and allowing the supports to feel a lower overall force. From test case 3.1 to 3.2, the stress in the hub decreased slightly, and this test case proved that filleting the hooks and the hub were the causes of the stress increase between case 2.3 and 3.1 and 3.2.
Test case 3 was used to analyze the custom components of the hydraulic system. The test involved having the welded regions for both brackets to be used as fixed supports and frictional contacts of 0.7 to be added between the pins and the brackets. The 0.7 frictional coefficient is the dry steel-to-steel contact. When the testing began, the simulation encountered divergence issues, and this was due to the applied force being greater than what the contact region for the fixed supports were able to handle. To fix this, the brackets were both thickened, so the frame mounting bracket was thickened from 3/4 of an inch to 1.5 inches, while the hook mounting bracket was thickened from 0.6 inches to 1.2 inches. The minimum factor of safety for this system was 4 because of the importance of the hooks not being able to slide off if the hydraulics snapped. The hydraulic components are made out of 1045 cold drawn steel, and its ultimate yield strength is 565 megapascals, which gives it ensures that there's a large gap before any components begin to fail in comparison to the 250 megapascals yield strength that was being used for the safety factor of other components for this system. Now, using this, the factor of safety showed that the frame mounting bracket was severely over-engineered with a factor of 13, while the hook mounting bracket and its respective pin were in a safe range. On the right here, you can see on the top, the frame mounting bracket. The middle would be the hook mounting bracket, and the bottom would be the pin on the hook mounting bracket. The assumptions made for this test was that the center pin hardware would be competent enough to hold the center pin to the frame securely. The input force used to actuate the hydraulic cylinder was 6,720 newtons, and the output force to the hook rod to move the hooks was 28,880 newtons. The shape of the connector allows the part to output a force 4 times greater than the input due to its leveraging abilities. The frictional contact coefficient used was 0.7 for all other components, excluding the pins that hold the system together. The factor of safety for the connector and the center pin are 1.5 and 1.53 respectively. This indicates that they are severely under-engineered for this system and will need to be reworked in the future to fit the safety factor. The hydraulic rods and cylinders were not tested because they are off-the-shelf parts, and they have already been approved to be appropriately rated to handle the forces required of them.
So the design analysis for our hydraulic system was heavily inspired by Q3 Heavy Lift's jacket lifting tool. The image for that is on the bottom right. You can see the way that the hydraulic system is extended and the lever arm is pulling in the hook on the jacket tool. Our hydraulic system uses the same concept. So the first design, it has the same type of lever arm, but the system is angled outwards to match the face of the hook. Now, obviously on the picture, it's not in line. Some number crunching was needed to put the hydraulic system in line. But when this design had been sent to the team, it was determined that this hydraulic system design wasn't going to work because the angle would have caused too much stress and a lot of other things, a lot of other problems. So we decided to go with another design. So the next design is the second stage, and this one is parallel to the frame, and it is also in line with the hook faces. The bracket supports are curved to the radius of the hook face so that it lines up perfectly. And you can see the lever arm here next to the frame face. And the hydraulic cylinders are alternating between the bottom flange and the top flange between each hook. So this design worked well, but it was determined that it needed some more support at the center pin on the connector, the lever arm. So then we go to stage 3. And our final design, although there's no picture, it has a pin bushing for the center pin. It looks just like stage 2. And the frame was also redesigned after the FEA results came back. So the frame had been adjusted, and so the hydraulic system had been adjusted as well to match with the frame.
This is the final assembled and model design. The major design components are shown and its functions are labeled. The new subsystem that was not in the initial model are the hydraulics, which serves to actuate the hooks. As noted, all the components on the frame are symmetric about the hub for the ease of design and assembling together the components when manufacturing. Since the materials used are all carbon steels, which does not have corrosion resistance, so a protection coating needs to be applied to the steel. All the steel will need to go through a galvanizing process, such as applying coating of zinc on steel to satisfy the corrosion resistance requirement. The final frame design and sizing can be seen in the drawing on the right. Overall, the dimension and geometry of frame remains constant. The major changes and additions are that the plate thickness are reduced to 1.5 inch since the frame was over-engineered and hand calculations was done to verify again. The frame is modeled in sections and welds added to resemble how the plates would be assembled during manufacturing. Lastly, about a 1 inch thick well, which is 70% of the steel plate thickness, is used around the connecting edge of the hub and frame to reduce stress concentration at that area. The final hook design and sizing can be seen in the drawing on the right again. Same as frame, the overall geometry and dimension remain constant. Thickness of hook is reduced from the initial design for a more optimal design, and the plate thickness varies. This design is modeled in sections of plates as well to account for manufacturing ability.
Our final design, you can see it here. You have the standalone hydraulic system at the bottom in a bronzish color. You can see that the pin supports, the brackets, are facing upwards, and they've got holes for screws to screw into the flange or the frame. And then you can see the pin bushing at the center pin on the lever arm, and then you can see the curved face of the pin brackets for the hook. Now there are 8 hydraulic systems in total, or 1 total hydraulic system with 8 hydraulics. And this is because we have 2 hydraulics per hook, and this is so we can cut the required force in half while keeping everything symmetric. The reason we didn't do the hydraulics on the top is because the whole arm connecting the frame is up there, the linear rails are up there, and everything would have kind of been in contact. There would have been too much stress if we did it up top, and there would have been too many things to keep track of. So
this is an animation video simulating the overall lifting operation.
our system evaluation for hydraulics, I tested the hydraulic system at 9,000 newtons. Our required force, our resultant force to actuate each hook was 6.7, approximately 6.7 thousand newtons, but I chose 9,000. Well, the 6.7 thousand was determined for one hook individually. So cut that in half, that's 3.35, 3.4. So I chose 9,000 to give it a factor of safety buff. And so that under simulation actuated the hooks extended in 10 seconds and retracts in 10 seconds, which is well above what we needed to do. And then I would suggest that when running the hydraulic system, do not go below 6.7 kilonewtons per hook to at least give it a factor of safety of 2. During simulation, for testing purposes, gravity was enabled, friction enabled, coefficient of restitution for collisions between parts, if there were any, there weren't. Contact groups to register collisions as well, there were none. And then, as I said before, the force in the simulation was 9,000 newtons in the hydraulic cylinder facing towards the frame or away from the hook, so that the hydraulic cylinder could retract to extend the hook and inversely extend to retract the hook.
Okay, so for section 9, last section I worked on was the system evaluation, more specifically the FMEA portion, or failure modes and effects analysis. So to help this be more comprehensive, the system was broken into 5 major sections. So with that in mind, the 5 sections are shown here as these 5 pictures. So we had the hooks, the frame, the linear rails and guides, hydraulics, and the lifting arm from the frame to the tower. Essentially, we use this as a practice from our decomposition to help us better understand and look at the components individually to make sure we are identifying all of the failure methods that could potentially be a problem within each one of those components. So here's a brief overview of what the chart looked like and how we based our categories. So for likelihood, we had a 1 to 10, consequence 1 to 10, hazard scores based off of likelihood and consequence, detections 1 to 10, and then risk priority number was our likelihood, consequence, and detection, which went up to a max of 1,000. So the failure mode focused on obviously the failure mode for that component, whether it's shearing, bending, etc. And the effect was, how does that failure mode affect the system as a whole? Would it, fall to the ground? Would it catastrophically disassemble? What's that look like? And then the mitigation was, how do we help reduce these risks that are associated with this problem? So you can see here the consequence and detection risk scales are over here on the side. For the likelihood, being that this at the point where we first started was more conceptual, and the fact that we're not actually building anything, all of our likelihood was based off of our FEA results. So basically, we had the highest rated as our highest stressed or highest area of concern within our FEA results. And then from there, we worked backwards to figure out what was the least. If there wasn't FEA, we went based off of research for the components, like for example, in some of the hydraulic components that were off the shelf, or the rails and carriages that were off the shelf. So like I said, due to the nature of the project, we didn't build anything. And with that in mind, we decided to perform the FMEA twice. So what we ended up doing was we did it in the initial design stage, and then we did it again following completion of the project. So during the initial design stage, it helped us identify areas from the initial FEA to work on further, whether that's geometry modifications, reinforcements, welding, or just areas that we want to do more precision in to figure out if it's an area that we really should be worried about if the results weren't super clear. So at the completion of the project, it helped us to reflect back on those changes, figure out if what we did worked or not, and kind of give us a thought process of moving forward in future projects. What's a good approach for it? So basically, because these charts were massive, I just went through and combined and figured out the average for the RPN for all the failure modes. So for the initial design stage, the average RPN worked out to about 145. Following completion of the project, the average RPN worked out to about 81. This works out to about a 56% reduction, which is pretty impressive considering this timeline was between these two tests was about a month and a half, 2 months this semester. So like I said before, performing this analysis helped us to identify critical areas and improve on them iteratively during the design. And then, like, for example, the largest one was the initial worst failure mode of the arm shear failure. These pictures here show the arm after adding the modifications, but we actually went back and added 2 different plates in these areas to help reinforce the arm in this area, along with changing the material of the arm and the geometry of the arm body itself. And with that in mind, our FEA results from the first time to the last time that we did our calculations on it ended up dropping significantly. So with that, we were able to reduce our likelihood, and the initial RPM from 490 dropped to 210, which is again about like a 57% reduction. So all in all, the FMEA was a very good tool set to use in our project. It helped us to identify areas of concern and stuff to work towards in our project, and then also allowed us to reflect back on the project at the end and figure out what worked, what didn't work, and areas of concern that we could work on or have potential future improvement on if the project were to move forward.
Hi, Sam here again to talk to you a little bit about the machine's reliability, safety, and including security. So let's discuss safety. With that, there must be a factor of safety. For this project, we are using 3, as mentioned in the previous slide, and because of the allowable stresses and OSHA guidelines, this design, when tested under different load phases, gave comparable results to other competitors. Next, designing with reliability in mind. Its material and other moving and static components were carefully considered. The effective use of material will make a lighter external arm and its weight influences the weight of the hook and the total weight of the structure. Lastly, with a simple lifting system and truss, it has only the ability to move horizontally, vertically, with limited rotation, and as a result, a structure such as this doesn't need much maintenance and very little human involvement for operation, which increases its security, safety, and reliability. Thank you.
From this project, the main significant accomplishment was being able to design a model in which all structural members fit the required factor of safety of 3 or higher. This table shows the factors of safety attained for all structural members. This model was successfully able to operate in inclement weather conditions with winds up to 20 miles per hour and was able to identify areas of concerns for future developers. Some of the open issues that are still present with this model are stress singularities in the carriages and rails. These were ignored because there was no solution found early in the modeling process, and ignoring these values is not entirely accurate, as there is no way to determine whether these structures would have experienced yielding or not. Sizing down components, the arm, frame, and hub are far above the required safety factor, and so there is a potential for system weight reduction if these components are minimized, if the size of the components is minimized. Reducing modeling time. Theoretically, this model should be divisible into multiple components. However, in all test cases reported for this project, the models were run using the whole assembly. Towards the end of the project, the top half of the model, specifically the frame and hub, were tested and had good coherence with the entire model. The bottom half was not tested by itself, and this could be an area of focus for improved design iteration speed.
To continue the open issues, for test case 3, it was found that the connector and center pin were under-engineered with safety factors of 1.5 and 1.53 respectively. The major issue with these components failing is that they're the attachment points for the hooks. So if any of the components snap, then the hooks are free to slide off the system, causing safety and damage liabilities. Now, due to time constraints on the project, another iteration wasn't able to be run. But in the future, if the rails could be blocked at the end of the frame to prevent this, that would be largely helpful. Continue the limitations. The last limitation is that the frame hub is fixed to the end of the arm, and the system can't move along the arm via a trolley system of some sorts. This means that the rocket would need to be in the same position every time, or the cargo pod door, like loading area, would need to be larger to accommodate the indifferences of the rocket being in the same position.
In conclusion, we just wanted to reiterate what the overall goal of the team was, which was to design a rapid loading system for speed and safety. And we were asked to create a design that quickly loaded cargo into an aerospace vehicle for rapid deployment within about 2 hours. And that short turnaround created a need for a simple lifting process and a reliable lifting mechanism to ensure that ample time is prioritized for loading the cargo board. And we believe that looking ahead, this project could always use some improvement to invoke more efficiency in the overall function of the design itself.